So today we're going to talk about radiation. Now, be slightly careful. Radiation comes up in a lot of different contexts within physics. So the word radiation is actually all over the place. But when we talk about thermal energy, when we talk about radiation, what we're really talking about are waves of infrared radiation, so electromagnetic waves of energy that are emitted by things that are hotter than their surroundings, okay, and will be absorbed by things that are colder than their surroundings. Okay, so we will come across radiation in other contexts, nuclear radiation and so on and so forth. It's just important to be aware of what is the context that we're specifically using this. So radiation in thermal energy refers to waves of infrared radiation. And so what will happen is all objects emit this stuff, okay, all the time. The difference is and it's also in the surroundings all the time. It's everywhere. The question is going to be is if you're hotter than your surroundings, you will emit more than you take in. You emit more than you absorb. If you're cold in the surroundings, then you absorb more than you take in and you give off. So what we tend to think of often is just the difference, the net difference. Are you something like in this image here? Are you like this fire, which is obviously a lot hotter than the surroundings, in which case you're dumping radiation into the surroundings, which enables a person to absorb that extra radiation and warm up. But of course, if that fire wasn't there, if we ignored the fire, then this person would become the thing that's emitting radiation out to the surroundings to cool down. So, yeah, all objects continually emit and absorb radiation. If they are hotter than their surroundings, they emit more than they absorb. Which means they cool down. And the reverse is true. If you're cold in your surroundings, you'll absorb more than you emit. And radiation, wonderful thing about radiation being a wave is there is no reason for any particles. So there are no movement of particles, no net flow of particles, which means that radiation is able to take place through a vacuum because it's infrared waves, which means that it means it. So radiation does not involve particles, so can take place in a vacuum, which is good for us because otherwise the sun would not actually heat us. There is no lead pipe that's connecting us to the sun for conduction, and there's not enough air or not enough particles in space to set up a convection current. Even space, even if you start saying, oh, it's not a perfect vacuum, it's just not enough. So to set up a convection current. So radiation is it. So all the energy that comes from the space to the Earth is going, via the sun. It's 150 million kilometers away, and it's reaching from the sun. We're getting about 1.4 kilowatts per square meter of space. We actually get quite a lot of energy from the sun, even though it's an enormous distance away. Now, obviously, we can feel radiation because we can stick our hands near something and feel warm. Remember, however, that our position is important because if you stick your hands above something, then you're going to feel, the thermal energy come from the convection current. Because, so if you stick your hands above something, this is where you're going to feel convection more than radiation. You'll feel both. So to the side is where you feel that sort of radiation. We can feel it, but you can't see it. in order to see it, we need an infrared camera. And I've seen stuff like this. They look like this. They give images that are like this. So when we're using infrared cameras, what we've got is something that is detecting detecting infrared radiation, and also tends to have, so an infrared camera tends to actually have two sort of lenses a lot of the time. So you'll have something which has, there'll be two lenses that are close by, and one is detecting visible light, which can give you an overall sort of shape of things, and the other will be an infrared camera. If you've got a very good infrared camera, you don't tend to need this, but what it enables us to do is to try and superimpose two images. And what we tend to do is then color them. This sort of image is called a thermogram, so or a thermograph, so a picture of thermal stuff. And what will happen is the hotter something is, the more radiation it emits, and so we tend to generally colorize that so it tends to look lighter, brighter. So in this one we've got sort of this boiling water coming out of a kettle, so this is colored very yellow. We've also got the hot water that's in there. We've got like the handle, so that's cold. We're not seeing much there. We've got the deer in the park that are emitting it, whereas the grass and things are in probably about about the same temperature as their surroundings, so they're absorbing the same amount around there, so we don't really get much from there. And then we've got this train, and what we can see with the train is we've got the train just pulled into the station. It's had to stop. So what's the warm bit? Well, it's around the brakes and the wheels, which is where all the friction is. So this bit is at a high temperature and is emitting lots of radiation, whereas sort of like the rest of the train is much cooler. Still warmer than the surroundings, because you don't want that to happen. And then you've got people. Now I want to zoom in on this person who's here, just to sort of make a little point. Now this person is actually, his core temperature is the same. He's 38 degrees. This is core body temperature. So, but we can actually see that we're not getting the same amount of radiation from him. And this is because obviously he's wearing clothes, which is a good thing to be doing when you're at a public train station. But what we can see is, where can we see a lot of radiation? Well, we can see it coming from his bare skin, from his hands. Where can we see? We can then see certain bits from sort of parts of his clothing that are probably a bit, more tightly fitting around his body. But then, like this bottom of his jacket here is not very warm at all. And so, what we actually also see, although this person is at a certain temperature, the things that he's wearing are going to change the amount of radiation we're going to see coming to our infrared camera from different parts of their body, which should make sense. That's one of the reasons one of the reasons that as humans we designed clothing was to keep ourselves warm, was to not dump a load of energy out into the atmosphere. And so this is sort of to be expected. But the key thing to remember is that one of the things we can see with all these people around here is that we're getting different amounts of radiation from different parts of their body. And what's different is not their temperature. Their temperature is not different. It's what they're wearing. And that will be, what color item are they wearing? Is it thick or thin? Like, what's the material made of? So the determination of the material that we've got actually can control how much radiation is coming out from something. And that is something that's quite is where we're going to really go with radiation. It's very easy to get this idea of, okay, hot things emit waves of energy via radiation, but actually we can control the amount that's coming out from something by selecting the materials we use to coat things in. And we're going to look in the videos a few little demonstrations that are going to investigate the importance of color with whether things will absorb radiation well or whether they will emit radiation well. So there is a link between, even things at the same temperature, we can control it by changing the color. And that's what the lesson video is. So have a watch of that.